Greeting of the day, I'm Rajkumar Parashari and I love doing physics. Today I'm here with the first part of the optical instruments. I will be covering working of an eye and its defect. To have the proper and in-depth understanding of the subject, you need to stay till the end of the video. And I would also like to suggest that please do subscribe my channel to get notification in time. An eye is nearly spherical, has unique and amazing internal structure which helps us to see world around us. So what you see is the cross-sectional view of an eye. The front side of an eye has a thin transparent layer called as the cornea. The thickness of this cornea is about 0.2 mm and has refractive index 1.376. Beneath the cornea, there is a dark round circle called as the iris. At the center of the iris, there is an opening called as the pupil. This is where the light enters, passes through the aqueous humor and falls upon the eye lens. Eye lens is held from all sides by the ciliary muscles with the help of suspensory ligaments. Light after refraction from the lens passes through the vitreous humor and falls upon the retina. The sensors on the retina, they converts optical signal into electrical signal which passes through the optical nerve and analyzed by the brain. In this slide, you see the normal eye and the ray diagram when the object has been kept at the far point. Normal eye means it is free from any defect and the far point means the object lies at infinity. Light ray traveling from infinity enters eye and refracted by the cornea as well as the lens system within the eye and is get focused at the retina. When object is brought closer and closer towards the eye, the focal length of lens eye system within the eye changes to ensure that image is always formed at the retina, which is about 2.5 centimeter from the lens eye system. Now the question is how this is possible. When the object is brought closer towards the lens, towards the eye lens, then the ciliary muscles contracts. Now as these contracts, the radius of curvature of the eye lens changes from both the sides to ensure focal length changes just enough and the image is formed at the retina. For the glass lens, the material used is glass. The radius of curvature from both the sides is fixed and so its focal length as given by the formula in this case when U changes, V also changes as F, the focal length is fixed. Just see this lens formula, 1 by V minus 1 by U is equals to 1 by F. Now as U changes, V also changes because focal length is fixed. And if we talk about the eye lens, then you will notice that the focal length of the eye changes because the ciliary muscles, they contracts just enough to ensure that the image is always formed at a fixed distance on the retina. So over here, as U changes, V remains fixed, which is about which is about 2.5 centimeter, as f is changed due to constriction of ciliary muscles. This particular discussion is related to accommodation power of eye lens. Look at these two images and focus on the ciliary muscles in the lens system. In the first case, the ciliary muscles are in the relaxed state. The eye lens is in the stretched state. Its curvature of side walls is less and has a greater focal length. In fact, the maximum possible focal length. And if we look at the another image, we'll notice the ciliary muscles are in the contracted state. The suspension ligaments are relaxed, and the side wall curvature is more. The focal length is less in this case. If we happen to see the front view of the ciliary muscles, we'll notice that when the eye is in the relaxed state, when the object is at the far off distance, then this is how the ciliary muscle should look like. The pink part stand for the ciliary muscles, and these lines, these radial lines, these are the suspensory ligaments, and the central circular part stand for the eye lens. The curvature is less, and the eye lens system has the maximum focal length. In the second case, object is at the near point, ciliary muscles are optimally contracted, and you can see, you can compare the size of the ciliary muscles in both the cases, and these suspensory ligaments, these will be slightly loose compared to this case, and the size of eye lens is shorter. Curvature is more, focal length is less. Now let us talk about the power of accommodation. So what power of accommodation mathematically means, this is what my focus is right now. In the first case, when the object is at the far off point, then the distance of the object, you already know, this is equals to minus infinity. V is equals to plus 2.5, and this is approximate distance, and focal length of the lens eye system is to be found. If we use the lens formula, 1 by f equals to 1 by v minus 1 by u, then we will get 1 by 2.5 minus 1 by minus infinity. So this is same as 1 by 2.5, and this implies f equals to plus 2.5 centimeter, because the focal length is plus 2.5 centimeter. So the power of the eye lens system, that will be given by the value, given by the expression P is equals to 1 by f. F should be in centimeter, and the unit should be diopter. So this is equals to 100 divided by 2.5 diopter, and this is equals to plus 40 diopter. So the power of eye lens system when the object is at far point is 40 diopter. You see, the focal length of the eye lens system changes, and hence we should be able to find out the power in extreme situations. And the first extreme situation happens to be when the object is at the far point, the power of the eye lens is plus 40 diopter. Now let's come to the other extreme situation. In this situation, the object has been placed at the near point of the object, and the distance happens to be 25 centimeter. Is that right? For this case, u is equals to minus 25 centimeter, v is equals to plus 2.5 centimeter. Let's try to find out the focal length in this case. You see, focal length in this case decreases, and over here let's use the lens formula. 1 by V minus 1 by U is equals to 1 by F. Let's see that what do we get as. So 1 by 2.5 minus 1 by minus 25 equals to 1 by F, or 1 by F equals to, take 25 as LCM, we'll get 10 plus 1, or we'll get F is equals to 25 by 11 centimeter. Now the power of the eye lens system in this case will be P dash, that will be equals to 100 by F diopter, and we need to put this F in centimeter, which we already have, and this is equals to 100 divided by 25 by 11. This is plus, so this is plus diopter, and solve it, will end up with plus 44 diopter. So the power of the eye lens system when the object is at near point is plus 44 diopter. So in the two extreme situation, when the object is at the far point, the power of the eye lens is plus 40 diopter, and when the object is brought closer to the near point, the power of the eye lens system happens to be 44 diopter. So the power of accommodation of normal eye is 4 diopter. I hope you understand what really it means. And further, if you want to talk about how the focal length changes, the focal length changes from 2.5 centimeter. I mean, this is the maximum value of the focal length of the lens eye system, to plus 25 by 11. Dear friends, wanted to draw attention to the fact that in this diagram, the position of the near point is not shown according to this scale, as the diameter of the eyeball is about 2.5 centimeter, and the distance of the near ball from the front side of the cornea is 25 centimeter, which is 10 times bigger than the diameter of the eyeball. This diagram does show the relative size of the eyeball and the distance of the near point from the front side of the cornea. Let us talk briefly about the range of vision of a normal eye and its power of accommodation. The range of vision of a normal eye is from infinity till the near point. When the object is at the infinity, ciliary muscles are in the most relaxed state. Eye lens has the maximum focal length and correspondingly minimum power equals to plus 40 diopter. When the object is brought closer, ciliary muscles, they keep contracting just to ensure that the image is always formed at the retina. When the object is brought at the near point, the ciliary muscles are in the most strained state and are optimally constricted. In this case, the eye lens system has the minimum focal length and correspondingly maximum power, given by the value P dash equals to plus 44 diopter. Thus, as object is brought from infinity to the near point, the focal length of the eye lens system changes, correspondingly power also changes, and the power of the eye lens system changes from 40 diopter till 44 diopter, and hence we say that power of accommodation of a normal eye is 4 diopter. Dear friends, I would like to draw attention to the fact, if the object is brought further closer to the eye, that is, if the distance of the object from the eye is less than 25 centimeter, say the object happens to be at a position O dash and distance is say 20 centimeter, the ciliary muscles will be in more strained state. Eye may be able to see the object, eye may be able to form its image at the retina, but eye will get tired quickly. If object is brought further closer towards the eye, image will not be formed at the retina and we will not be able to see the object. Now the eye defects. The main eye defects are number 1, myopia, also called as short-sightedness. Second is hypermetropia, also called as far-sightedness. Then you have the presbyopia, and fourth is astigmatism. So we will discuss mainly myopia and hypermetropia. Maybe we'll have a short discussion on presbyopia as well as on astigmatism. So why we call myopia as short-sightedness? Because in this case the person is able to see the objects lying close to him, but he is unable to see far off objects. And for the case of hypermetropia, the person is able to see far off objects but is unable to see the objects lying close to him. And this is diagram of a person who is suffering from myopia. When the object is at the near point, the ciliary muscles, they will be optimally constricted and these will be in most strained state. Image will be formed at the retina. When the object is at the infinity, when the rays are coming from the infinity, the eye lens system is not able to focus these rays at the retina. In fact, these rays, they focus before. Now the question is, why the eye lens system is unable to focus rays coming from the infinity at the retina? The answer to this question is the ciliary muscles, they lose their partial ability to regain their relaxed state. 7 centimeter. Though the ciliary muscles, they lose the ability to regain their relaxed state fully, but they do regain a bit. Corresponding to that, we have the new far point. In the case of normal eye, the far point was at infinity, but for the myopic person, the new far point is much closer. And it may be, for example, in my case, this distance, the new far point is 40 centimeter away from the eye. So I am able to see all the objects lying between 25 centimeter and 40 centimeter with clarity. So my range of vision is restricted between 25 centimeter and 40 centimeter. So let's try to find out what is now the power of accommodation. The power of accommodation for a myopic person can be calculated as follows. When we consider object to be at the near point, then u is equals to minus 25 centimeter, v is equals to plus 2.5 centimeter, and the focal length of the lens eye system can be calculated using this formula. 1 by f is equals to 1 by v minus 1 by u, and this is equals to, we have already this is equal to 1 by 2.5 minus 1 by minus 25, and this is equals to 11 by 25. This implies that f is equals to 25 by 11 centimeter, and the power in this case will be, power of eye lens system will be plus 44 diopter. Now let us take let's try to calculate power corresponding to the new far point. Corresponding to new far point, the value of u is equals to minus 40 centimeter. I am taking my case. My new far point is only 40 centimeter away from the eye, and the v got to be plus 2.5 centimeter only. Now let's calculate the focal length, the new focal length of the lens eye system. We know that the slave muscles, they are not able to regain their original relaxed state, but they do regain a bit. So whatever they regain, corresponding to that, the focal length will be given by 1 by f is equals to 1 by v minus 1 by u, and this is equals to 1 by 2.5 minus 40. Let's take 100 as LCM. If we take 100 as LCM, so this will be 40 plus 2.5, and this implies the new focal length f is equals to 100 divided by 100 divided by 42 42.5. Now the power will be given by, the new power will be given by 100 by f in centimeter, and the unit got to be diopter. So this is equals to 100 divided by plus 100 divided by 42.5, and this is equals to 42.5 diopter. So for this myopic person, in fact, in my case, the power of accommodation of my eye is, you see, I mean, this ranges from 44 diopter to 42.5 diopter. So the power of accommodation in my case, power of accommodation in my case is 1.5 diopter. Is that right? And for different individuals, new far point will be at different places. For example, in my case, if it is 40 centimeter, for other cases it could be 60 centimeter, 50 centimeter, and so on. Now let's see that how the myopia could be corrected. This myopia can be corrected by putting a concave lens of appropriate focal length. What really it means is how this correction is possible. Let's try to discuss. You see, the focal length of this concave mirror is such that when the object is at the infinity, you see, I mean, this myopic person cannot see the object lying at infinity with clarity. And why it cannot see with the clarity? We already know that the rays coming from the infinity, they focus before the retina. Is that right? Now in this case, when we use the corrective lens, which is the concave lens in this case, rays coming from the infinity after the refraction from the lens. Can you see that these rays, these are diverging a bit. These are diverging before falling on the eye lens system. Now you see, if we extend these diverging rays, they tend to meet backward at a point. Is that right? Now you see, the focal length of this new corrective lens is such that these rays, they meet at the new far point. Is that right? Now you see, the myopic person, I'm taking my case, so I am able to see all the objects lying between near point and the new far point. Now I'm unable to see all the objects lying at very, very far or at infinity. So why I am able to see the objects lying at infinity? Because this concave lens, helps us to make the image of the objects lying at infinity at the new far point. Is that right? So the role of the concave lens is to make the image of far off objects at the point where I can see with clarity. Is that right? And this is how the eye lens helps us to see far off image with clarity. And this is how the corrective lens works. Now let's try to calculate power of this lens in my case. In my case, I have already shared that my new far point is 40 centimeter in front of the lens. Is that right? Now you see what really it is doing. The object is at the infinity. So u is equals to minus infinity centimeter, and what it does, it makes the image of this object at the new far point. So v is equals to minus 40 centimeter. Let's calculate the focal length of this concave lens. The focal length of this concave lens can be calculated using the lens formula 1 by f equals to 1 by v minus 1 by u. This is 1 by minus 40 minus 1 by minus infinity. So the focal length is minus 40 centimeter. So the focal length of the corrective lens should be minus 40 centimeter, and the power of this corrective lens, is equals to 100 by f in centimeter, and the unit is diopter. Let's substitute the value. This is 100 divided by minus 40 diopter, and this is equals to minus 2.5 diopter. So the power of corrective lens I should be using is, the power of the corrective lens should be minus 2.5 diopter. So I have a numerical, NCERT numerical for you, and in this NCERT numerical, the far point of a myopic person is 80 centimeter. Far point, you see, for the normal eye, the far point is infinity, but for the myopic person, the far point has come closer, and the far point is 80 centimeter. So this is I. This happens to be the optical axis of eye lens. This is near point of the eye, and this happens to be the new far point. And according to the problem, this new far point is at 80 centimeter, and near point is always 25 until otherwise given. So over here, so what is power of lens required to enable him to see a very distant object? So this myopic person want to see a far off object. Object is at infinity. This is where the object is. So the u is equals to minus infinity, and person will be able to see this object provided he uses the corrective lens. Is that right? And this, what this corrective lens will do? This corrective lens will make the image of this object at new far point. Is that right? So v over here is minus 80 centimeter. Calculate the focal length using the lens formula. This is 1 by v minus 1 by u, and this is 1 by minus 80 minus 1 by minus infinity 1 by f. This is infinity. So this further implies f is equals to minus 80 centimeter. So this should be focal length of the corrective lens used. Is that right? Minus sign clearly suggests the lens used is the concave. Now the power of this lens is 100 by f diopter, and this is equals to 100 divided by minus 80 diopter, and this is equals to minus 1.25 diopter. So that makes what is the power? What is the power of lens required? We know the power of lens required is 1.25 diopter. If I ask in this problem, so what is the range of vision for this person? The range of vision for this person is between 25 centimeter and 80 centimeter. Is that right? Now see the second case. In what way the corrective lens help the other person? You see, the corrective, what is the role of this corrective lens? The role of corrective lens is, you see, is to make the image of the object at a place where the person can see with clarity. Person cannot see object lying at infinity with clarity. Person can see at the new far point. Person can see the object lying at new far point. Is that right? So what this lens does, it makes the image of this object is at the infinity. This lens, concave lens, it makes the image of this object at new far point, and this is how this corrective lens helps the person to see the object lying at very far off point. Does the lens magnify the distant object? Of course not. It doesn't magnify, but definitely it brings the object much closer to the eye at the new far point. Let us discuss the case of a person who is suffering from hypermetropia. A person who is suffering from hypermetropia can see the objects lying at far off points with clarity. As you see in this diagram, if the object lie at the far off point, then the eye lens system is able to focus it at the retina, and of course because the rays they focus at the retina, he will be able to see the object with clarity. When the object is kept at the near point, the eye lens system is unable to focus the rays at the retina. In fact, in this case, the rays they converge behind the retina, and hence this person suffering from hypermetropia will not be able to see this object with clarity. Now the question is why this happens so? This happens so because these ciliary muscles they lose the ability partially to contract. In the process, the eye lens system is not able to form the image at the retina, and this leads to a situation in which the near point of a person shifts little away from its actual position. The far point of the person suffering from hypermetropia still remains the same. Is it right? So what really I mean is the near point of a person with normal eye lies at 25 centimeter, but for a person who is suffering from hypermetropia, the near point shifts little away from the eye, say take it to be 40 centimeter for the sake of example, the range of vision for the normal eye, that is from 25 centimeter till infinity. But for a person who is suffering from hypermetropia, the range of vision is from near point till infinity. For this particular example, the near point is at 40 centimeter. So the range of vision for this person is from 40 centimeter till infinity. This person should be able to see all the objects lying beyond 40 centimeter. But the objects lying within 40 centimeter, he or she should not be able to see. Now let us try to calculate the power of accommodation in this case. When the object is at infinity, u is equals to minus infinity and v is equals to plus 2.5. Let's try to calculate focal length of the lens eye system in this case. This is equals to 1 by v minus 1 by u, and this is equals to plus 2.5 centimeter, and this will lead to the power of eye lens system. When the object is at infinity, this should be plus 40 diopter. Now you see, when the object is considered at near point, in that case u is equals to minus 40 centimeter, v is equals to plus 2.5 centimeter. Now let's try to calculate focal length in the new context when the object is considered at the near point. So let's use the lens formula. 1 by f is equals to 1 by v minus 1 by u, and this is equals to 1 by 2.5 minus 40. So that will make it plus. Take 200 as LCM. Now as you take 200 as LCM, this will be 5, and this will be how much? This will be 80. This will be 80. 1 by f, and this implies that 1 by f is equals to 200 divided by 85. 200 divided by 85. So f is equals to 85 by 200 centimeter. Now the power, this is equals to 100 by f diopter, and this is equals to 100 divided by 200 divided by 85 plus sign, and this is equals to 42.5 diopter. You see, so in the two extreme cases, the power happens to be 40 diopter and 42.5 diopter. So the power of accommodation in this example, power of accommodation in this example should be equals to 2.5 diopter. Let us see how eye defect hypermetropia can be corrected. Hypermetropia can be corrected by choosing a convex lens of appropriate focal length. What this convex lens does, it makes the image of an object at a place where the person can see, and we already know that this eye can see all the objects those lie at near point and beyond. But this eye cannot see object lying at the near point. Is that right? So the role of this convex lens is to make the image of this object at the near point. So let's see that for this case, U is equals to, I'm talking about for this lens. For this lens effectively touches the cornea. So this U is equals to minus 25 centimeter. Is that right? And this is the object and its image is formed at near point. So V should be equals to, I'm taking for this case of clarity, to be 40 centimeter. It will be different for different individuals. This is an example I have chosen. Now let's try to calculate focal length of this corrective lens. The focal length of this corrective lens can be calculated using the lens formula. So this is equals to 1 by minus 40 minus 1 by minus 25. So that makes it 1 by 25 minus 1 by 40, or 1 by F equals to, take 200 as LCM. This is 8 minus 5. So F is equals to plus 200 by 3 centimeter. Now power of this lens, the power of this convex lens used, corrective lens used, should be equals to 100 by F diopter, and this is equals to 100 by 200 by 3 diopter, and this is equals to plus 1.5 diopter. So this is the power of the corrective lens required. Now let's try to see the associated numerical. So this is numerical. The near point of an hypermetropic person is 75 centimeter from the eye. So near point is 75 centimeter. So this is near point. Let's try to visualize it. This is eye. This is the principal axis of the eye lens. This is near point, and this is near point. U is equals to minus of 25 centimeter, and V is equals to minus 75 centimeter. I wish I could have written this after putting a convex lens. You see the role of this convex lens. We know that to make the image of an object at a place where I can see with clarity. Is it right? So this is the position of the eye and its image is formed at near point. So what is the power of the lens required? The power of the lens required can be calculated using the lens formula. 1 by F is equals to 1 by V minus 1 by U, and this is equals to 1 by V. V is minus 75 minus 1 by minus 25. So this is 1 by 25 minus 1 by 75, and take 75 as LCM. This is 3 minus 1, and this implies that F should be equals to 75 by 2 centimeter. Now the power of the corrective lens used should be equals to 100 by F, of course in terms of diopter. So this is 100 divided by 75 by 2 diopter. Solve it, and this is equals to 100 multiplied by 2 divided by 75 diopter. This is 25 3s are 75, and this is 4, and this is equals to plus 8 by 3 diopter, or plus 2.66 diopter. So thank you so very much for being with me patiently, and if you want to get notification in time, I will suggest that you should subscribe this channel of mine. This is the place where you will get the insight of the subject. This is the place where you get the real physics. So thank you so very much. God bless you.